Hello everyone and welcome to a video on random processes and discrete time LTI systems. So in this video we're going to study what happens when we put a real wide sense stationary random process x of n into a discrete time LTI system with impulse response h of n, and we get out y of n, which is another wide sense stationary random process. So we're going to try and predict some of the characteristics, specifically the mean and the autocorrelation of the output process. For this video, we're assuming that we have a zero mean input process. It's also independent and identically distributed. So they're independent from time point to time point and identically distributed at each time point. So for this IID process, sometimes known as a white noise process, it has an autocorrelation, Rx of L, where L is the lag, that is equal to sigma x squared delta of L. Sigma x squared is simply the variance of this white noise process, and you see that the autocorrelation is zero everywhere except at lag zero, where it's equal to sigma x squared, which is the variance of the process. And so the two questions we're going to try and answer in this video are, what is the mean of y of n, the mean of the output process, and what is the autocorrelation of the output process, i.e. we're going to try and calculate Ry of L. So first we're going to try and find the mean of the process, and we have to remember the relationship between the input and the output for a discrete time LTI system. And the input and the output are simply related via convolution. So y of n is equal to the convolution of x of n and the impulse response h of n. And so using that relationship, we can actually go ahead and find the mean. So the mean is the expected value of y of n. So that will be the expected value of the output of the convolution, which we can write as the sum over k. K is just the intermediate variable of x of k, h of n minus k. So this is just simply the convolution sum for as a way to compute y of n. Now, the only thing that's random in here are the x's, and so we can bring the expectation inside. Remember, h of n is deterministic, so that's not assumed to be known here. So we'll bring the expectation inside, so it's just the sum of a bunch of expectations now. So the sum k equal minus infinity to plus infinity, expected value of x of k times h of n minus k. Okay, well, we know that this process is zero mean, which means the expected value here is 0. Whoops. So the expected value here is 0. So what we have is this will just be equal to 0. So the mean of the process is simply 0. So if I put in a zero mean signal, to an LTI, discrete time LTI system, I will get out a zero mean signal. Nothing in this calculation assumed anything about h of n other than it's deterministic and we know what it is. In this part of the problem, we're going to determine the autocorrelation of the output sequence, Ry of L, given the autocorrelation of the input sequence. And for this specific example, we're going to assume a simple two-point finite impulse response system that's sketched here, and it can be written delta of n plus delta of n minus 1. Now we know for an LTI system that the input and the output are related via convolution, so we can write y of n is x of n convolved with the impulse response, delta of n plus delta of n minus 1. So this is a very simple convolution to do. The convolution of x of n with a single delta function is just x of n. And the convolution of x of n with a shifted delta function is just a shifted version of x of n. So we can see that for this specific system, the output is just the sum of the current input and the previous input. And so that allows us to simplify an expression for Ry of L. Now, just as a reminder, Ry of L is the expected value of y of n times y conjugate of n minus L, We don't have to worry about the conjugate because the input is a real random process, the system is real, so the output has to be real. So the conjugate is there for the definition, but we don't need it. And the other thing to notice is that if we compare these two, right, L is the difference in these two indices. So it's n minus L gives us positive L. And we'll use that fact as we write this out. So we can write Ry of L, now just substituting in this expression for y of n, we can write it as Ry of L is the expected value of x of n plus x of n minus 1 times x of n minus L plus x of n minus L minus 1. And that's just substituting in, this is y of n, this is y of n minus L. So now I have the multiplication of these two, so I can multiply this out. It'll be the expected value of x of n times x of n minus L plus x of n times x of n minus L minus 1 plus, now I'm doing this times these two, x of n minus 1 times x of n minus L plus x of n minus 1 times x of n minus L minus 1. So hopefully what you can see here, well, first of all, this is the expected value of a sum. So it's the expected value of a sum, which is just the sum of the expected values since the expectation is linear. And so this will be the expected value of x of n times x of n minus L. Well, that's just Rx of L, right, by the definition. So the first term is Rx of L. Now the second term, now we've got an n here, but we have an n minus L minus 1. So this is going to look like Rx of something, right? What's the lag here? It'll be n minus L minus 1. So this is plus Rx of, now I'm going to n minus n, let me write that out more clearly, n minus L minus 1. I'm just trying to determine the difference between these two indices, right? It's n minus this one, okay, and I'll reduce that in a second. And then I'm going to do the same thing here, right? So I'm just going to get different versions, shifted versions of Rx for each of these. So this next one will be Rx of n minus 1 minus n minus L plus Rx of n minus 1 minus n minus L minus 1. Right, so I can reduce all of these. I've just written them out so that I can clearly see that I'm computing the difference, right? I'm computing the lag, the difference between these two. So reducing it all, it comes down to the first one is Rx of L plus Rx of the n subtract off, and this will be a minus, so this will be L plus 1 plus, now this will be the n subtract off, this will be negative L minus 1, sorry, positive L minus 1, so Rx of L minus 1 plus, and now the last one here, subtract off, there's an n minus 1 in both cases, so this will just be Rx of L again. Okay, so we can see two of these will combine. Whoops. These two will combine. So I'll be left with 2 Rx of L plus Rx of L plus 1 plus Rx of L minus 1. So what we can see here is this is just 2 times this. And then I'm going to add in 1 times Rx, but now shifted to the left by 1, and this is 1 times Rx shifted to the right by 1. So over here I could sketch Ry of L it will just look like this. At 0, it'll be 2 sigma x squared. At 1, it'll be sigma x squared. At -1, it'll be sigma x squared. And everywhere else, it will be 0. So that's what this equation here is telling us. And we just got this by substituting into the definition and carrying out all the algebra. So now we have a nice expression here for Ry of L. And so now we notice, look, the input is uncorrelated, right? It's an IID, it's independent. It's an independent process. So independent, they're definitely going to be uncorrelated. So that's why this is a single delta function at lag 0. Now, once we put them through this system, they become correlated. Why do they become correlated? Because now the output at each time is the input at that time plus the previous input, right? So that is going to give us some correlation, but it's only correlated out to a single lag, right? Out at lag 2 and -2, you've got 0 correlation, and it continues 0 outside these intervals. Okay, so now we have an expression for Ry of L. Now, in class, we discussed a general expression for how to compute the autocorrelation for the output of an LTI system, given the autocorrelation for the input, when you know what h of n is. And this general expression we derived was Ry of L is equal to Rx of L convolved with h of L convolved with h conjugate of -L. And so for this particular system that we have, Rx of L is sigma x squared delta of L, and we would convolve that with h of L and h of -L, right? And if we did this convolution with this, then we would get exactly what we just got from the definition. So we have 2 ways to solve this problem. The way on the previous page, we use the definition and h of n for this system. And here we use this general expression that the textbook discusses and that we've discussed in class. So there were multiple ways to solve this problem, but we end up with the same solution. And that solution tells us that the output will be correlated at a lag of 1, right? So the current output is correlated, partially correlated with the 2 nearest neighbors, but uncorrelated outside of that, because at lags greater than 1, it goes to 0. So this is the summary that we have for this particular example that we did. We started with an IID process, right? A white noise process going into an LTI system. And we solved for both the mean of the output of that system and the autocorrelation at the output of that system for a particular system that we assumed, right? And this is the general expression that we would have gotten, assuming the IID or white noise process going in. The output autocorrelation will simply be sigma x squared times h of L convolved with h conjugate of -L. And the mean is 0 if the input mean is 0. So we've answered the questions that we set off to answer. And hopefully built some skills working with autocorrelations and LTI systems as we did it. Thanks for watching.